think are important and will be useful to you. So let's start the question real quick. So now I'm done kind of chatting it all up. Let's just really go for it. So it starts with this dart exiting the I don't know what you want to call it, the tube. That's what they call it, right? The tube question. So here's the tube. And it's got like a little round opening there at the front. And we have our dart. Here's the dart. Exits the tube at velocity v, mass m, and this is length L. Now, they make it, the problem seems like it's really about the dart, but we know the dart's going to have a collision. And as you read the text of the question, you realize that after the collision, the dart's going to slide, the dart and the block are going to join together. So clearly a perfectly inelastic collision. And then after they join together, more is going to happen. We know that the dart and the block are going to slide across the table and eventually come to rest, which really means that this isn't what the problem is about. The problem is actually about many things. That's just part A of the problem, right? That there's going to be a part B somewhere or other where the dart is going to strike and become embedded in the box, and the box and the bullet are going to have some combined velocity I'll call V final, for lack of a better term. And then there's also going to be this part where the box and the dart will have combined together and slid across the table until they've come to rest under the action of gravity. I'm sorry, I said gravity. Under the action of friction. So it will have slid a distance d. This really represents the question. So although they've drawn a bit of a picture of the initial conditions of the problem, there's definitely a lot more going on. Now, I don't have to read very much about the problem to note that if it leaves at velocity v and has an inelastic collision, then there's going to be something related to conservation of momentum. I don't need the problem to tell me that, and I'm not even sure what it's asking yet. I'm not even looking at that part yet, but that has to be true. And moreover, they tell me it's acted on by friction, which means there's going to be a force in this direction, friction, while the box is sliding to rest. They give me mu, so I know that force is going to be mu times m plus m times g. That's the force of friction that acts on it. I don't need the problem to give me any information to know that that has to be true. Now, I know that the frictional force is constant. This is important. Here's where I want to start looking at that sheet of yours. I'm writing these things out not knowing what the question's about. I'm writing these things out because these are things that are called to mind when I'm starting to think about the nature of the question. So let's read more of the setup. It says a constant force is exerted on the dart of mass m in the horizontal direction as it moves through the tube of length L. That's incredibly important. It doesn't seem like it. Now remember, you don't get to write on the screen. You don't get to annotate the test at all. But they said constant force. I'm going to write that down, constant force. Because that creates an entire chain of events. And here's what I'm going to switch back to the gallery mode so I can see all of your faces. This is so ridiculously important because it's one word, constant. But the moment they said constant force, they mean constant acceleration. This is where that sheet comes in. Constant force means constant acceleration. Constant acceleration means you can use Galileo's motions equations. It means that the work done is just force times distance. It means that the change in momentum is just force times time. And since I can get work or impulse, that also means that the work done is the change in kinetic energy. It also means the impulse is the change in momentum. Ella's having a conversation with somebody. Somebody's totally interrupting her. And it's a happy conversation. I can tell because she's got her happy face on. So you guys follow that, right? So when I look across here, I realize that there's two constant forces acting on the system. One is the force that's in the tube, and one is the frictional force. When I look across here, I also notice that they are very fixated on length for both of those. So I am immediately drawn to the idea that the work here is going to be the change in kinetic energy. They have force and distance as work. And work here, change in kinetic energy. It's brought to rest. I know where it started. So I haven't looked at the question part yet. I'm just looking at the implications of knowing that a constant force acted on the system 2 different times, and there was an inelastic collision in the middle. That's all I've done, but it gives me a lot to go on. So whatever they're going to ask me about how these things are related, I probably have a lot to go on now that I didn't have before. So let's look at the question. It says, this sentence has problems, so I'm going to do my best. Students experiment with a variety of tubes because students just have tubes laying everywhere. Assuming that air resistance is negligible and that all other parts of the experiment remain the same, should the students use a long tube or a short tube to make the stopping distance d the longest? Justify your answer. Now, I've read about 8 of your responses, and I would love to pull a bunch of them up now just for fun, but it won't be fun for some of you because you're going to see that what you wrote, not going to work. And there's a couple of things here that I need to be very clear about. Saying that you need to make the tube longer isn't enough. It's not even close. In fact, this is a 4-point question right now. And in order to get those points, saying that the length of the tube has to be longer gets you 1 out of 4 points. So all of you wrote the tube has to be longer. What you have to do in your response is answer the question. And the question asked how the length of the tube is related to d. You have to explain that. That's the justification. And trust me when I say your readers are going to be looking to see if you connect all the dots together. This is an AP1 response. We talked a lot about this in AP1, the idea that you have to connect the dots together. What that means is you have to explain to the grader that you know how one thing leads to the next. You can't just assume that when you say, well, a longer tube means it'll be traveling faster, that's enough. That would get you the second point. So if you say making the tube longer, you're going to get 1 point. If you're saying making the tube longer would mean that the dart would leave at a faster velocity, that's probably going to get you the second point. But they're probably going to say, well, how do you know? Well, if it's in the tube longer, it experiences a force for a longer period of time and is now going faster. All right, now you've secured point number 2 because you indicated why the longer tube makes the dart travel faster and you used a physics representation to do so. You can say if the tube is longer, more work is done. Greater change in kinetic energy. Fine, perfect, great. You have linked it to a physics relationship. So now on that sheet you're writing out, you have to do that for everything that's related. So now that I know the velocity is greater, what does that do? Well, that means a faster velocity for the dart will mean a faster velocity for the dart and the block after the collision. If everything else is the same, if I increase this, I must increase that. That's point number 3. Because now you can indicate that the constant force to slow it down will require a longer distance because it's traveling faster when it strikes the block. So to get all 4 points, you had to connect all 4 of the dots together. That's hard to do. And do you have to do any math? No, but yes. Look, you have to know how the increase in frictional force is going to require an increase in distance. Do you need to write it out mathematically? No. But it would be helpful. I mean, look, you can simply say this times d has got to equal the change in kinetic energy. Has to. We know that now we have a way of writing how the final velocity is related to the initial velocity. And over here, well, that's going to be F times L equals 1/2 mv squared. Right? I'm saying this because although I didn't need to do this, the next question is, students derive the following equation for the distance. And the equation they have is FLM over m plus m squared mu g. Now, you might feel compelled to show if this is true, but you don't have to. The question they ask is, without algebraic manipulation, all right, I did all that for nothing. Without algebraic manipulation of the equations, explain whether this equation accurately matches your explanation in part A. This question was only worth 2 points. But do you know that most people are only going to gain 1 point here? Because saying that L increases D isn't enough. You do have to say yes or no whether it agrees. It does. But you also have to indicate mathematically how. You could say that there's a direct proportion between L and D. That would be enough. Direct proportion means when one increases, the other increases. You can say that L and D are both in the numerator. Fine. That's fine. That'll do it. That'll let them know that if L gets bigger, D gets bigger. You can say it's a linear relationship if everything else is held constant. Now, do we know whether this equation is correct or not? No, I see things in it. Like, for example, I see mu mg, right? It's right in here. I also see this, because there's an m here and another one of those m plus m's in the denominator. And I see F times L. I mean, I see all the pieces I come to expect. Do I know if they're going to form up in this way? No, I have no idea. No idea if it's going to work out. I'd have to work it out to see. But you don't have to. You're not being asked to do that. In fact, the moment this part of the question is done, we go on to the next part, and it totally yeets all this out of the way. So I want to pause for just a minute and remind us about something. Find a way to bridge the way we would have looked at solving this problem before with what we're going to have to do now. So I think, yeah, have some scratch paper out. Sketch out what you think is going on this problem. Even if none of this makes it into your actual work, what you've got is kind of the foundations of the things that will contribute to the question. And that's going to help you, I think, quite a bit. Now, moving on in this one, I think this part of the problem threw a lot of people. And it's a little disappointing because it's not as hard as it seems, but it's hard. It made me even, harder in ways you weren't ready for. It says that there's a new force or tube or something. I'm going to erase that, or at least hide a lot of it for a minute. It says, students then change the force so that it can be described as a function of position. Can anybody, tell me any other force that you know about that's a function of position? Go ahead, Jason. Yep, that's it. Springs. Hooke's law. A function of position. So, knowing about springs and knowing that they are a little different, the force is not constant. So suddenly motion equations are gone and force times distance is no longer the work. The question goes on to say, explain how the students could use the equation given above to find the launch speed of the dart if the length of the tube is 2 meters. It seems like it's a numerical question, but it is not. How would you find the launch speed of the dart? You have force and you have a total distance. So let's go back through our knowledge base. Do we know anything that links force and distance to velocity? And the answer should be, oh, well, yeah. Our definition of work allows for any force to be used to determine the change in kinetic energy. That is the work-energy theorem. It doesn't work just for constant forces. It works for any force, even if that force changes. In fact, especially if that force changes. In fact, I think to answer this question, all you really have to state is that, well, you're going to integrate. Integrate the expression for the force from 0 to 2 meters. That will give you the change in kinetic energy of the dart. That's not the whole thing, though. You have to go a little further because it says, explain how students could use the equation to give the launch speed of the dart. So you'd have to go one step further and indicate that once you have the energy, you could solve for the velocity. You couldn't stop at saying the energy because then you're assuming, and you can't assume, that the graders know that you know that the kinetic energy is related to the velocity. You can't make that assumption. And they'll smack you down for it. And then the problem goes on. Predict what will happen to the launch velocity of the dart if the length of the tube was doubled, and justify your answer. Now, this is the part where, you either do the integration, you put in the 12x, or you recognize that it's like Hooke's law. Either one of these is going to get the points, but we are now we're past the getting a 4 territory now. Once we got that problem, once we nailed this 12x part and recognized what was happening here and started answering that and acquired a couple of the points, we made it onto the other side of the 8-point part of the curve, which means we're in 4 territory. Definitely past the 3 territory. Want to get up to a 10 because that guarantees a 4. So this question, predicting what will happen to the launch velocity of the dart if the length of the tube was doubled, could easily be answered if you remember that the energy stored in a spring is 1/2 kx squared. Or you could integrate. Either way, they're hoping that you'll remember that if you double the tube, you'll get 4 times the energy. But they asked about the velocity. So although you get 4 times the energy, this kinetic energy has the velocity squared. So if you double the length of the tube, you're still only going to get twice the velocity. Right? Because this is still going to lead to just 1/2 mv squared. It's the recognition that if you double this, well, yeah, you'll double that because they're both squared. You follow me there? That one's going to be harder to get the points for because you have to remember this. Now you'd get that if you'd integrate it. If you go over here and integrate, you'll get the 1/2 times f, times x squared. Times x. And then you can drop your 12x in there and get 1/2 times 12x times x. So you'll get the 6x squared. You'll get that. So you can do the math part, but they don't want the math part, but they want the result of the math part. Now, if you put this in there, if you type the equations out and say these things, like when you integrate the 12x with respect to x, you get 6x squared. You can type all that in a simple statement. Doesn't need any fancy typing to get that. You guys know how to type that in, but you didn't need to. And we're about to run out of time. So this is where, I would have liked to get to the end of this, which is students are given an equation for the launch velocity of the block as follows. And I want to cover that with you guys. So I'm going to wait till Monday. This also gives people who haven't had a chance to go in and work this out to go work it out.